Okay, so in this question, we're going to be looking at omega. So it's going to be talking about the upper bound of the rate of growth of a function. So this is the definition of omega here. And we're asked to use this definition to prove this statement. So let me rewrite this as, for every function f and g, such that every natural number maps to a positive real number, including 0, if g is in the big O of f, then f is in the omega of g. Okay, so let's try proving this. So first, we deal with this. So, actually, this whole thing. So we let f and g be arbitrary functions. Oops. Okay. And we assume that g is in the big O of f, and we should unpack this, which means that there's a C1, I'm going to use C1 and N1 here, because, we don't want to get these terms mixed up. So there's a C1, N1 that's a positive real number, such that for every natural number, if n is larger than or equal to n1, then, and we pause for a second and think about this, so we're saying Gn, okay, so it's standard definition, then Gn is smaller than or equal to C1 times f of n. Okay, and then we want to show this last part here. So we want to show that f is in the omega of g. Okay, what does that mean? So let's take this definition here. F is in the omega of g. Okay, so let's write C2 and N2 here. Okay, and okay, n is then or equal to n2, then okay, and then this part would be following the same guidelines here. It's easy to be confused, so we have f of n is greater than or equal to c g of n, and this is C2. Okay, then first we need to know that this statement is true by the assumption, but we don't have access to it yet. So let's just let C1 and 1 positive real numbers such that it satisfies assumption. Okay, and then if we let n be a natural number, assuming that n is larger than or equal to n1, then we know that Gn is smaller than or equal to C1 times f of n. Okay, that much we know. Then we want to prove this statement here. So this is an existential here, so we have to choose C2 to be something, and we have to choose N2 to be something, and we can ignore that for now. This part we already have quantified. We assume that n is larger than or equal to 2 and 2, and then we want to show this part here. So we take what we have, make our assumption, and we have this statement here. So let's rewrite this. C1 times f of n. Then we want to manipulate it somehow to make it like this. First of all, we can multiply both sides by 1 over C1, which we have access to because up here. So here, 1 over C1, this crosses out, which is good. Okay. Then, okay, so then we can rewrite this as then f of n. Okay, we're getting pretty close. The only thing is that the only difference between this and this down here is this term. Well, we can wrap this term into a variable called C2. So here we let this, and then n2, we can just select 1. Usually 1 works because we only have to find one value such that it works, right? So then we have our proof.